Earth seems like an unshakable sanctuary. We live out our entire existence underneath a soft blue sky, protected by a thick, life-sustaining atmosphere, wrapped in a gentle magnetic shield, and warmed by a steady, middle-aged star. It is easy to look up at the peaceful night sky and imagine that the rest of the universe shares this serene harmony. But that peaceful image is a comforting illusion. Beyond the quiet boundaries of our atmosphere lies a dark, violent, and utterly unforgiving cosmos. The universe is not a tranquil garden built to nurture life. It is a vast, pitch-black wilderness governed by extreme forces that defy human imagination, a realm where physical laws are pushed to their absolute limits, creating worlds that resemble actual cosmic nightmares. Out there in the deep void, there are alien planets where the rain is made of razor-sharp liquid glass, carried by roaring winds that move faster than the speed of sound. There are worlds where skies rain molten iron, where giant oceans of glowing lava cover entire hemispheres, and where the air itself is composed of vaporized rock. We have discovered planets that are darker than asphalt, absorbing almost every speck of light that strikes them, and lonely worlds cast out from their solar systems to drift forever through the freezing pitch-black void. Today, we will explore the dark side of the cosmos, the most terrifying planets and worlds ever discovered by science. If you enjoy embarking on deep journeys into the mysteries of space, please consider liking this video and subscribing to the channel. Also, leave a comment down below telling us where in the world you are watching from and what time it is right now. Now step away from the warmth of our blue sky, leave behind the safety of Earth, and let us plunge straight into the dark, terrifying depths of deep space. When we think of bad weather on Earth, we picture heavy thunderstorms, hurricane-force winds, or blinding blizzards. Yet, even the most violent natural disasters on our home planet are gentle compared to the atmospheric horror taking place across the Milky Way. Across the vast expanses of deep space, meteorology operates on a scale so extreme that weather ceases to be a simple shift in temperature and instead becomes a weapon of absolute destruction. Atmosphere, pressure, and thermodynamic forces combine to produce liquid glass, vaporized metals, and corrosive acids that rain down from alien skies. Our first stop in this tour of fatal weather takes us 63 light-years away from Earth to the deep blue world known as HD 189733b. At first glance through a powerful space telescope, this distant exoplanet appears strangely familiar. It shines with a brilliant deep cobalt blue color, closely resembling the tranquil oceans of Earth as seen from orbit. But this azure appearance is a deadly optical trap. The blue hue does not come from vast expanses of liquid water, nor does it stem from a calm, oxygen-rich atmosphere. Instead, it is the result of a scorching atmosphere composed primarily of hydrogen, helium, and suspended particles of silicate glass. HD 189733b belongs to a class of exoplanets known as hot Jupiters. It is a giant gas world that orbits exceptionally close to its parent star, at roughly 1/30th of the Earth-Sun distance. Because of this extreme proximity, the planet completes a full orbit in just over 2 Earth days, and its atmosphere is heated to temperatures exceeding 1,700 degrees Fahrenheit. This intense stellar heating drives thermal circulation on a planetary scale. The daytime side of the planet is continuously scorched, while the nighttime side attempts to radiate that heat back out into the void. This massive temperature differential generates extreme global winds. On HD 189733b, winds howl across the surface at speeds approaching 5,400 miles per hour. That is nearly 7 times the speed of sound, making these winds roughly 20 times faster than the strongest winds ever recorded on Earth. At these speeds, kinetic energy transforms atmospheric molecules into relentless battering rams. But the wind itself is only the transport mechanism for something far more lethal. The extreme heat on the day side vaporizes the silicate minerals present in the planetary crust and atmosphere. As these vaporized silicates are swept toward the cooler night side by supersonic winds, they cool rapidly and condense into tiny particles of solid glass. The howling winds pick up these glass particles, turning them into a perpetual global storm. Because the atmospheric circulation moves horizontally around the planet at supersonic velocities, the rain on HD 189733b does not fall downward from the sky, it rains sideways. An observer standing on this world would not merely be soaked, they would be blasted by billions of microscopic glass daggers travelling at 7 times the speed of sound, shredding anything in their path in a matter of milliseconds. While HD 189733b represents the terror of glass-laden supersonic winds, we do not need to travel 63 light-years into the deep void to find a world plagued by lethal weather. Right here in our own solar system, sitting directly next door, is a planet that serves as a grim warning of runaway atmospheric breakdown: Venus. Venus is often described as Earth's twin due to its similar size, mass, and bulk composition. Millions of years ago, Venus may have possessed liquid oceans and a far more hospitable climate. Today, however, it is the most inhospitable planetary surface in the solar system. The culprit is an extreme runaway greenhouse effect. The atmosphere of Venus is exceptionally thick, composed of more than 96% carbon dioxide. This dense blanket traps solar heat with terrifying efficiency, pushing surface temperatures to a uniform 870 degrees Fahrenheit, hot enough to melt solid lead, zinc, and tin. The surface atmospheric pressure on Venus is about 92 times Earth's sea level pressure. Standing on the Venusian surface would feel equivalent to being submerged more than 3,000 feet beneath the ocean on Earth. The air itself is so dense that it behaves almost like a heavy fluid, distorting light and creating a crushing weight that would instantly flatten human lungs and metal structures alike. Above this scorching high-pressure furnace sits a perpetual deck of dense clouds, located roughly 30 to 40 miles above the ground. These clouds are not made of water vapor like those on Earth. Instead, they are composed primarily of droplets of concentrated sulfuric acid. As chemical reactions occur in the upper atmosphere, sunlight interacts with carbon dioxide, water vapor, and sulfur dioxide to generate a continuous supply of concentrated acid. This produces a relentless cycle of acid rain. Heavy drops of sulfuric acid fall from the cloud layer, cutting through the hazy skies. However, because the lower atmosphere is so blindingly hot, a unique phenomenon occurs before the acid can ever reach the ground. As the raindrops descend into the searing lower air, the extreme heat causes them to evaporate mid-flight, a process known as virga. The sulfuric acid turns back into corrosive vapor, floating upward to recondense in the cooler upper atmosphere and repeat the cycle endlessly. Even though the rain never touches the dry, cracked volcanic rock below, the atmosphere remains saturated with volatile sulfur compounds, creating an endless loop of chemical corrosion that destroys anything entering its skies. If glass winds and sulfuric vapors represent one level of atmospheric terror, the far reaches of exoplanetary research reveal worlds that push chemical meteorology into the realm of the unbelievable. Consider the extreme world known as WASP 76b, located roughly 640 light-years away in the constellation Pisces. WASP 76b is another ultra-hot Jupiter, but its environment is vastly more extreme than that of HD 189733b. It orbits so close to its parent star that it completes a full revolution in less than 2 Earth days. This ultra-close orbit locks the planet in a state of tidal locking, meaning that one side of the planet perpetually faces the burning light of its star, while the other side forever faces the dark, frozen vacuum of space. The day side of WASP 76b is bombarded by relentless stellar radiation, driving surface temperatures to an astonishing 4,000 degrees Fahrenheit. At these temperatures, normal chemistry breaks down completely. Molecules are ripped apart into their constituent atoms, and elements that we normally think of as solid metals on Earth exist purely as vaporous gases. On the day side of WASP 76b, iron does not exist as a solid, nor as a liquid pool. It evaporates into the air, rising up into the atmosphere as iron gas, blending seamlessly with hydrogen and helium. This creates a dramatic contrast with the night side of the planet. While the day side boils at 4,000 degrees, the night side, forever shielded from the star, is significantly cooler, dropping to roughly 2,700 degrees Fahrenheit. While still incineratingly hot by human standards, this temperature shift is large enough to trigger massive physical transformations in the atmosphere. Fierce global winds are generated by the immense temperature difference between the light and dark hemispheres. These winds scoop up the vaporized iron gas from the blazing dayside and sweep it across the terminator line, the boundary zone where perpetual day meets perpetual night. As the iron gas crosses into the cooler night side, the temperature drops below the condensation point of iron. The iron gas cools rapidly, condensing first into dense clouds of liquid iron droplets, and then falling out of the sky as heavy metal precipitation. On the night side of WASP 76b, the weather report calls for torrential downpours of liquid iron. Glowing red drops of molten metal fall through the dark, violent clouds, pooling in vast metallic streams before being swept back toward the dayside to evaporate once more. These worlds demonstrate that weather across the cosmos is not merely a variation of rain, snow, and wind. It is an expression of thermodynamic power operating at the outer limits of physics. From supersonic storms carrying clouds of jagged glass on HD 189733b, to the crushing acidic furnace of Venus, to the molten metal downpours of WASP 76b, the atmospheres of deep space remind us that the gentle rains of Earth are an incredible cosmic rarity. When we analyze planets across the universe, temperature ceases to be a simple measure of hot or cold and becomes a fundamental force that alters the structure of matter itself. In the gentle cradle of Earth, temperatures fluctuate within a narrow range that allows liquid water to exist and chemical bonds to remain stable. But across the broader canvas of deep space, planets are pushed to thermal limits so extreme that they challenge our understanding of planetary physics. At one end of this spectrum are ultra-hot worlds, where heat tears molecules apart into basic atoms. At the other end are frozen realms sitting near absolute zero, where entire atmospheres freeze solid and rain down as nitrogen snow. To understand the terrifying upper limit of planetary heat, we must look at Kelt 9b, an exoplanet located 670 light-years from Earth in the constellation Cygnus. Kelt 9b holds the title of the hottest known exoplanet in the universe. It is a gas giant nearly 3 times the mass of Jupiter, but its physical properties are warped beyond recognition by its extreme proximity to its host star. The host star, Kelt 9, is a massive blue-white star that burns at temperatures nearly double those of our Sun. Kelt 9b orbits this searing stellar furnace at a distance 30 times closer than Earth orbits the Sun, completing a full orbit in just 36 hours. Because of this extreme proximity, the planet is tidally locked, leaving one hemisphere permanently exposed to the relentless glare of its star. The daytime hemisphere of Kelt 9b reaches an astonishing temperature of nearly 7,800 degrees Fahrenheit. To put this number in perspective, the surface of Kelt 9b is hotter than the surfaces of most stars in our galaxy, including red dwarfs and cool stars. It is hotter than the melting point of every known element and compound on Earth, including tungsten, titanium, and carbon. At 7,800 degrees Fahrenheit, the rules of planetary chemistry break down through a phenomenon known as thermal molecular dissociation. On standard gas giants like Jupiter or Saturn, the upper atmosphere is composed of complex molecules like water vapor, methane, and ammonia. On Kelt 9b, the thermal energy is so intense that chemical bonds cannot survive. The heat violently shakes molecules apart faster than they can form. Water, methane, and carbon dioxide are completely shredded into their constituent individual atoms. Even sturdy diatomic molecules like hydrogen gas are torn apart into isolated hydrogen atoms on the dayside. The atmosphere on the dayside does not consist of gases in any traditional sense, but rather a glowing atomic haze composed of individual atoms of hydrogen, helium, iron, and titanium. The intense ultraviolet radiation pouring from the host star strips electrons from these heavy metal atoms, creating an atmospheric gas infused with ionized iron and titanium vapor. This ionized metal gas absorbs incoming stellar radiation with extreme efficiency, heating the atmosphere even further in a runaway thermal cycle. Furthermore, This intense thermal energy drives a process of planetary evaporation. The gas on the day side is heated to such extreme kinetic energy that the planet's gravity can no longer hold onto it. The atmosphere expands dramatically, bloating the planet to almost twice the radius of Jupiter, despite having a similar density. This expanding envelope of atomic gas is continuously blasted away into space by stellar winds, leaving a glowing tail of ripped-away planetary material trailing behind the planet like a giant cosmic comet. Kelt 9b is literally being cooked alive, its very substance ripped apart atom by atom as it slowly dissolves into the vacuum. If Kelt 9b represents the ultimate cosmic furnace, the opposite end of the thermodynamic spectrum reveals worlds frozen in a state of absolute silent paralysis. Deep in the outer reaches of planetary systems, far beyond the warmth of any parent star, lies the realm of extreme cold. A primary example of this frozen extreme is the distant world OGLE 2005 BLG390LB, located over 20,000 light-years away near the center of the Milky Way galaxy. This planet orbits a dim, low-mass red dwarf star at a distance that keeps it permanently starved of light and heat. OGLE 2005 BLG390LB is a rocky world roughly 5 times the mass of Earth, but unlike our vibrant planet, it exists in a state of deep thermodynamic stagnation. The surface temperature of OGLE 2005 BLG390LB drops to a crushing negative 370 degrees Fahrenheit, only about 50 degrees above absolute zero, the theoretical point at which all atomic motion ceases. At these temperatures, heat is entirely absent, and the physical behavior of volatile compounds changes completely. On a world this cold, atmospheric dynamics are reversed. On Earth, liquid water evaporates into water vapor, forms clouds and falls back down as rain or snow. On OGLE 2005 BLG390LB, elements that we normally recognize as light gases, such as nitrogen, methane, and carbon monoxide, cannot exist in a gaseous state. The thermal energy is simply too low to keep the molecules moving. As a result, the atmosphere of OGLE 2005 BLG390LB undergoes a continuous process of deposition, skipping the liquid phase entirely to freeze directly from gas into solid form. The entire atmosphere freezes out of the sky. Thin, ghostly clouds of nitrogen and methane form in the faint light, condensing into delicate crystals that fall silently onto the surface as frozen nitrogen snow and methane ice. Over millions of years, this process covers the planet in thick sheets of clear, rock-hard nitrogen ice, forming deep glaciers that sit above a dark mantle of frozen stone. There are no liquid oceans, no wind currents, and no geologic activity driven by surface warmth. The landscape is completely locked in time, a frozen monument where time itself seems to stand still under the dim light of a dying red sun. Even within our own solar system, the distant dwarf planet Pluto and its neighbour Triton offer a glimpse of this icy terror. On Triton, the largest moon of Neptune, surface temperatures drop to negative 391 degrees Fahrenheit. Here, geysers of liquid nitrogen spew from beneath frozen crusts, driven by subsurface pressure, only to instantly freeze as they hit the air, falling back down as solid frost in a vacuum-like sky. These thermal extremes highlight the delicate balance required for life. Whether ripped apart into a glowing plasma of heavy metal atoms at 7,000 degrees on Kelt 9b, or frozen into absolute crystalline immobility at negative 370 degrees on OGLE 2005 BLG390LB, matter pushed to its thermal limits leaves no room for liquid water, organic chemistry, or survival. These worlds demonstrate that heat and cold are not merely weather conditions, but violent geological and physical architects that redefine what a planet can be. Most planets in the universe enjoy a predictable, stable existence. They are bound by the unyielding grip of gravity to a central host star, tracing the same oval path through space for billions of years. This stellar anchor provides warmth, light, and a steady, rhythmic drumbeat of seasons. But deep within the galactic dark lies a vast, hidden population of worlds that have been stripped of this cosmic anchor. These are rogue planets, lonely, starless wanderers ejected from their birth systems, left to drift forever through the pitch-black void of interstellar space. Rogue planets are born in violence. During the early, chaotic stages of planetary formation, young solar systems are crowded battlegrounds. Dozens of protoplanets slide around their host stars, competing for orbital space and sweeping up primitive gas and dust. In these densely packed celestial environments, gravitational interactions are complex and unpredictable. When a large gas giant like Jupiter or Saturn shifts its orbit, its massive gravitational field can act as a giant sling. A smaller protoplanet, or even a fully formed terrestrial world that strays too close, can be caught in a gravitational slingshot. Instead of settling into a stable orbit, the smaller world is violently accelerated, pushed past the escape velocity of its star system, and cast out into the interstellar abyss. Once ejected, a rogue planet enters a nightmarish perpetual exile. Without a star to orbit, it has no day or night, no spring or summer, and no concept of a year. It travels through the cold cosmic vacuum at speeds of hundreds of miles per second, wrapped in absolute, unbroken darkness. The nearest stars are distant, needle-thin pinpricks of light that offer no warmth whatsoever. One of the most enigmatic of these wandering ghosts is CFBDSIR 2149-0403. Located roughly 130 light-years from Earth, this world is estimated to be between 4 and 7 times the mass of Jupiter. Because it does not orbit a host star, astronomers cannot detect it through traditional methods like measuring the periodic dip in starlight as a planet passes in front of its sun. Instead, CFBDSIR 2149-0403 was discovered by capturing its faint infrared thermal signature against the freezing background of deep space. While CFBDSIR 2149-0403 has been drifting in total isolation for hundreds of millions of years, it is far from frozen solid in its interior. When giant gas planets form, the immense mass of gas contracting under its own self-gravity releases vast amounts of gravitational potential energy as internal heat. Furthermore, the decay of primordial radioactive isotopes deep within its core continues to generate significant thermal energy. As a result, CFB-DSIR 2149-0403 maintains an internal core temperature of nearly 700 degrees Fahrenheit. This creates a hauntingly bizarre atmospheric environment. From the outside, the planet appears completely black, sailing silently through the void. But as you draw closer, its upper atmosphere reveals a dim infrared glow. Swirling storm clouds composed of iron dust, hot silicate grains, and trace amounts of methane roll across its surface, driven solely by heat rising from its deep interior. Without stellar light to illuminate these atmospheric storms, the entire planet exists as a glowing, turbulent phantom, radiating its own dying internal energy into the cold darkness. Another prominent example of these drifting nomads is PSO J318.5-22, a young rogue planet located about 80 light-years away in the constellation Capricornus. PSO J318.5-22 is roughly 6 times more massive than Jupiter, but it is only 12 million years old, a mere baby in cosmic terms. Because it is so young, it retains a tremendous amount of its initial heat of formation. Its surface temperature hovers at a scorching 1,500 degrees Fahrenheit. Spectroscopic measurements of PSO J318.5-22 reveal a choked, chaotic atmosphere filled with thick clouds of molten iron droplets and scorching mineral dust. High-altitude winds whip these metallic clouds around the planet at extreme speeds, generating global dust storms of hot liquid metal that churn without end. Yet, despite these ferocious atmospheric dynamics, there is no sun to light up the sky. The storms rage in absolute pitch blackness, illuminated only by the faint, eerie red glow of the planet's own heat and the distant, cold stars of the galactic rim. while gas giant rogue planets like CFBDSIR 2149-0403 and PSO J318.5-22 are easier for astronomers to detect due to their large thermal signatures, computer simulations suggest that rocky, Earth-sized rogue planets are vastly more common. Estimates indicate that there may be billions or even trillions of Earth mass wanderers drifting between the stars in the Milky Way alone, outnumbering normal stars in our galaxy. What would an Earth-sized rogue planet look like? As it is ejected from its native solar system, its surface temperature plunges rapidly. Within a few thousand years of losing its sun, its oceans freeze solid from the surface down to the seabed. The atmosphere, once rich in nitrogen, oxygen, or carbon dioxide, cools to the point where it collapses entirely, freezing onto the icy surface as a thick shell of solid snow. Yet, despite this surface death, the interior of a rocky rogue planet can remain hot for billions of years. The decay of radioactive elements like uranium, thorium, and potassium in its silicate mantle continues to generate geothermal heat. This thermal energy flows outward, melting the bottom layers of the global ice crust and creating vast, dark, subsurface oceans of liquid water beneath miles of impenetrable ice. In these pitch-black subsurface oceans, far beneath the frozen, airless shell of the planet, hydrothermal vents could spew hot, mineral-rich fluid into the water, powered entirely by the planet's internal heat engine. Isolated from the cold vacuum above, protected from lethal cosmic radiation by thick layers of ice, primitive microbial life could theoretically thrive in total darkness, blissfully unaware that its planetary home is hurtling through the empty void of interstellar space, billions of miles from the nearest star. These starless wanderers remind us that the universe is not merely a collection of neatly organized solar systems. It is also an ocean of pitch-black space, populated by billions of ghost planets, lost worlds drifting forever through the dark, carrying the dying embers of their creation into the infinite void. Light is the primary lens through which we observe and understand the cosmos. When we gaze upon planets through optical telescopes, we expect them to shine by reflecting the starlight that strikes their atmospheres and surfaces. Bright clouds of water ice, vast polar caps of carbon dioxide, and reflective silicates give most worlds a visible presence against the black backdrop of space. However, deep within the universe, astronomers have uncovered a class of exoplanets that break this fundamental expectation. These are ultra-dark worlds, planets that absorb almost every single photon of light that falls upon them, plunging them into a state of absolute ink-black darkness. The most extreme example of this phenomenon is TRES 2b, an exoplanet located roughly 750 light-years away in the constellation Draco. Discovered by the Transiting Exoplanet Survey Network, TRES 2b holds the record as the darkest known planet ever identified in the observable universe. To visualize just how dark this world is, consider common materials on Earth. Freshly fallen white snow reflects roughly 90% of incoming sunlight, giving it an albedo, or geometric reflectivity, of 0.90. Charcoal, one of the darkest natural substances on Earth, reflects about 4% of incoming light. TRES 2b, by contrast, reflects less than 1% of all light that hits its atmosphere, making it significantly darker than acrylic paint, coal, or asphalt. It is, for all practical purposes, a spherical black hole of light orbiting a distant star. Understanding why TRES 2b is so profoundly dark requires a deep dive into atmospheric chemistry and quantum physics. TRES 2b is a gas giant roughly the size and mass of Jupiter, but unlike Jupiter, it orbits its host star at a terrifyingly close distance of just 3 million miles. This extreme proximity heats the planet's upper atmosphere to over 1,800 degrees Fahrenheit. At these scorching temperatures, the planet cannot form reflective cloud decks made of water vapor, ammonia, or methane, which give Jupiter its bright, swirling bands of white and orange. Instead, the intense thermal environment leaves the upper atmosphere completely clear of reflective condensates, allowing light to penetrate deep into the gaseous envelope. Once light travels into the atmosphere of TRES 2b, it encounters a dense mixture of vaporized alkali metals, specifically sodium and potassium gas, along with gaseous titanium oxide and vanadium oxide. These gaseous elements possess atomic structures that are extraordinarily efficient at absorbing visible light. In basic quantum terms, when photons of visible light strike gaseous sodium and potassium atoms, the electrons orbiting these atoms absorb the precise wavelengths corresponding to red, yellow, green, and blue light, jumping to higher energy states. This absorption is so comprehensive across the entire visible spectrum that almost no light manages to bounce back out into space. The sodium and potassium act as a massive chemical sponge for photons, trapping incoming starlight and converting its electromagnetic energy directly into heat. Furthermore, the immense density of the atmosphere creates a phenomenon known as Rayleigh scattering suppression, where light is absorbed long before it can be scattered by atmospheric molecules. However, calling TRES 2b completely invisible is not entirely accurate. While it absorbs more than 99% of all visible starlight hitting it, the planet is not a flat black circle against the stars. Because its atmosphere is cooked to nearly 2000 degrees Fahrenheit by its host star and trapped solar radiation, the planet glows with its own internal thermal emission. If a human observer were to approach TRES 2b in a spacecraft, the planet would not appear as a solid black sphere. Instead, it would look like an ominous, dark ball of coal burning from within. The atmosphere emits a faint, sinister red glow, similar to the dull illumination of a dying furnace burner or a hot coil on an electric stove. Swirling currents of incandescent gas move silently across its dark face, driven by thermal gradients between the day and night sides. This thermal radiation is shifted heavily toward the infrared spectrum. While our human eyes can only register the faint red wavelengths emitted by the hottest atmospheric layers, an infrared camera would show a brightly glowing world, radiating immense thermal energy into space. The planet continuously converts the absorbed visible light from its star into high-energy heat, which it then bleeds out slowly as long-wave thermal radiation. TRES 2b is not an isolated anomaly. Astronomers have identified several other ultra-dark hot Jupiters, such as WASP-12b and HD 209458b, which display similar light-absorbing traits due to high concentrations of vaporized sodium, potassium, and metal oxides in their cloudless upper skies. These worlds challenge long-held planetary models that assumed gas giants would always possess highly reflective atmospheric clouds. These realms of absolute darkness serve as a stark reminder of how exotic planetary physics can become under extreme cosmic conditions. In these mysterious corners of deep space, chemical elements that we view as solid metals or basic salts on Earth are transformed into vaporous light traps, swallowing the rays of nearby stars and leaving behind pitch-black worlds that burn with a silent crimson fire. Gravity is the fundamental architect of the cosmos, holding galaxies together, steering planets along precise orbital paths, and guiding the birth and death of stars. In balanced solar systems like our own, gravity acts as a gentle, stabilizing hand. But when a planet strays too close to a massive, dense star or a black hole, gravity ceases to be a force of order. It transforms into an unyielding engine of destruction. At close range, the difference in gravitational pull between the near side and the far side of a world generates immense tidal forces. These forces can pull solid rock apart like soft putty, distort spherical planets into egg-like shapes, shred planetary crusts, and melt entire worlds into raging oceans of molten lava. To witness this gravitational distortion in its most extreme form, we must journey to WASP-12b, a doomed gas giant located approximately 1,400 light-years from Earth in the constellation Auriga. WASP-12b is a hot Jupiter, roughly 1.5 times the mass of Jupiter, but its orbit is terrifyingly tight. It circles its yellow dwarf host star at a distance of less than 2 million miles, so close that it completes a full orbit in just 26 hours. At this hyper-close proximity, WASP-12b sits dangerously deep within its star's intense gravitational well. Gravity decreases with the square of distance, which means the side of the planet directly facing the star experiences a vastly stronger gravitational pull than the side facing away. This difference in force across the diameter of the planet creates extreme tidal stress, pulling the world outward along its orbital axis. Instead of remaining a smooth, round sphere, WASP-12b has been stretched into a distorted, oblong shape resembling a massive American football or an egg. The planet's self-gravity, which normally holds its gas in a tidy sphere, is simply not strong enough to resist the immense differential pull of the host star. This gravitational stretching has pushed WASP-12b past its Roche lobe, the theoretical boundary within which a celestial body's material remains gravitationally bound to itself. Because the planet has overflowed its Roche lobe, its outer atmosphere is no longer held by the planet's own mass. The star's gravity is actively stripping material away from the planet's swollen upper atmosphere at a staggering rate of nearly 200 quadrillion tons of gas every year. This stolen atmospheric material streams continuously away from WASP-12b, forming a massive glowing ring of gas and plasma that wraps around the host star. Astronomers watching WASP-12b are not just observing a planet, they are watching a planet being eaten alive. Orbital calculations indicate that this relentless gravitational cannibalism will completely consume WASP-12b in less than 3 million years, a mere blink of an eye in cosmic time. While WASP-12b illustrates how tidal forces can warp a gas giant and strip away its atmosphere, solid rocky planets subjected to extreme gravitational proximity suffer an even more visceral fate. Consider Corot 7b, a rocky world located about 480 light-years away in the constellation Monoceros. Corot 7b was one of the first super-Earths ever discovered, a rocky planet roughly 5 times more massive than Earth. However, any resemblance to Earth ends with its density. Corot 7b orbits its parent star at a distance of just 1.5 million miles, 23 times closer than Mercury orbits our Sun. It completes a full year in less than 20 hours. Because Corot 7b is so close to its star, it is tidally locked. The side facing the star is subjected to relentless radiation and extreme gravitational squeezing. This intense proximity creates massive tidal friction within the planet's interior. Just as the Moon pulls on Earth's oceans to create tides, the enormous gravity of Corot 7b's host star flexes and kneads the solid interior of the planet as it orbits. This continuous gravitational flexing generates immense internal friction, producing heat that melts the planet's mantle from the inside out. Combined with the searing heat pouring down from the nearby star, the daytime surface of Corot 7b is transformed into a global ocean of boiling liquid rock. There is no solid ground on the day side of Corot 7b. Instead, vast churning seas of liquid basalt and iron cover thousands of miles, reaching temperatures exceeding 3,600 degrees Fahrenheit. The intense heat causes the rock itself to evaporate into the atmosphere, creating clouds of silicon monoxide and sodium vapor. When these heavy mineral clouds drift toward the cooler night side, they condense and rain down as solid gravel and liquid magma, feeding back into the molten oceans below. An even more extreme example of gravitational destruction is found on K2-141b, a super-Earth located roughly 200 light-years away. K2-141b orbits its star so closely that more than 2/3 of the planet is locked in perpetual daylight. On this world, tidal forces and intense radiation create a lava ocean over 60 miles deep, with supersonic winds reaching speeds of over 3,000 miles per hour, whipping vaporized rock across its jagged surface. The gravitational forces operating on these worlds highlight a fundamental boundary in astrophysics known as the Roche limit. The Roche limit is the minimum distance to which a celestial body, held together only by its own gravity, can approach a second, more massive body without being torn apart by tidal forces. If a planet, moon, or asteroid crosses inside the Roche limit of a larger body, the differential gravitational force pulling on its front and back halves exceeds the internal gravitational binding energy holding the object together. When this threshold is crossed, the body cannot maintain its structural integrity. The crust cracks, deep fissures tear open across the mantle, and the entire planet begins to disintegrate. In the final stages of Roche limit disintegration, a world is pulverized into billions of fragments. These fragments do not fall all at once. Rather, they spread out along the planet's original orbital path, forming a vast, glowing debris ring of dust, shattered rock, and iron vapor around the host star. Over millions of years, the star gradually accretes this ring of planetary remains, swallowing every last trace of the world that once existed. Gravity, the very force that allowed these planets to coalesce from clouds of primordial dust billions of years ago, ultimately becomes their executioner. Whether warping giant worlds into distorted gas eggs like WASP-12b, liquefying rocky crusts into deep magma oceans like Corot-7b and K2-141b, or shredding worlds into glowing rings of debris, extreme gravity demonstrates that no planet can withstand the merciless pull of a close stellar neighbour. When a massive star reaches the end of its nuclear life cycle, it does not go quietly into the cosmic night. It detonates in a cataclysmic supernova explosion, blasting its outer layers across light years of space and collapsing its core into an object of unimaginable density, a neutron star. Among these stellar corpses, the most extreme are pulsars, superdense stellar remnants compressing the mass of an entire sun into a sphere no larger than a city. Rotating hundreds of times per second and generating magnetic fields trillions of times stronger than Earth's, pulsars act as cosmic lighthouses, sweeping concentrated beams of deadly electromagnetic radiation and relativistic particles across the void. For decades, astronomers assumed that the chaotic violence of a supernova would destroy any surrounding worlds. Yet, in an ironic twist of astronomical history, the very first exoplanets ever confirmed were not found orbiting a warm, golden, sun-like star. In 1992, astronomers Alexander Volshin and Dale Frail discovered 3 alien worlds orbiting a rapidly spinning pulsar designated PSR B1257+12, located roughly 2,300 light-years away in the constellation Virgo. These worlds, later named Drauga, Poltergeist and Phobetor, exist in a haunting realm governed not by the gentle thermal light of a living sun, but by the relentless, lethal pulse of a dead stellar corpse. To understand the nightmare environment of a pulsar planet, one must first consider the violent origin of these worlds. It is extraordinarily unlikely that these planets survived the initial supernova explosion that created PSR B1257+12. Any primordial atmosphere or ocean would have been instantly vaporized, and the sudden loss of stellar mass during the blast should have hurled original planets out into deep space. Instead, scientists believe these worlds are second-generation planets, born from the radioactive ashes of the destruction. Following the supernova, a dense fallback disk of enriched heavy elements, silicates, carbon, and heavy metals encircled the newly formed pulsar. Over millions of years, this radioactive dust cloud coalesced into solid, rocky worlds, doomed from their inception to orbit a dying engine of high-energy radiation. Orbiting a pulsar means living under a constant, crushing bombardment of ionizing radiation. PSR B1257+12 rotates once every 6.2 milliseconds, spinning over 9,000 times every single minute. With each rapid rotation, its immense magnetic field accelerates charged particles along its magnetic poles, blasting out intense beams of high-energy X-rays, gamma rays, and powerful radio waves. As these focused radiation beams sweep across the orbits of Drauga, Poltergeist, and Phobetor, the surface of each world is repeatedly struck with high-energy photons every few milliseconds. The physical consequences of this continuous high-energy bombardment are catastrophic for any potential chemical complexity. On Earth, our atmosphere and magnetic field shield us from mild solar ultraviolet rays, allowing complex organic chemistry to remain stable. On a pulsar planet, the incoming radiation consists of high-energy X-rays and gamma-ray photons, capable of penetrating deep into rock and atmosphere alike. When an X-ray or gamma-ray photon collides with an atom, it violently knocks electrons out of their orbital shells, a process known as photoionization. This ionization breaks the delicate covalent bonds holding chemical compounds together. Complex organic molecules, carbon chains, and amino acids are instantly ripped apart into simple charged ions. If any double-stranded genetic structure, like deoxyribonucleic acid, were introduced to this environment, the incoming high-energy photons would induce thousands of double-strand breaks per second. The molecular backbone of life would be shredded faster than any biological or chemical repair mechanism could operate. Cellular structures would be pulverized at the fundamental atomic level, rendering the formation or survival of organic life impossible. In addition to direct photon radiation, pulsar planets are blasted by a relentless phenomenon known as a pulsar wind. Because a pulsar spins at such extreme speeds, its rapidly changing trillion Gauss magnetic field acts as a massive electromagnetic accelerator. It drags free electrons and positrons from the stellar surface and accelerates them to near the speed of light, creating a continuous relativistic particle wind that pours outward into the planetary system. When this relativistic pulsar wind slams into the atmosphere of an orbiting planet, the kinetic and magnetic energy transfer is devastating. The high-energy electrons and positrons strike atmospheric gas molecules, transferring momentum and heat while stripping away electrons in a process known as impact ionization. Over time, this energetic particle bombardment heats the upper atmosphere to extreme temperatures, causing gas molecules to reach escape velocity and blow off into space. Unless a pulsar planet possesses an impossibly strong internal magnetic field, its atmosphere is gradually eroded away, leaving a bare, exposed husk of shattered rock. Yet, despite this absolute biological dead zone, the visual environment of a pulsar world would be hypnotically, hauntingly surreal. Because the pulsar emits almost no visible thermal light, the sky on a planet like Poltergeist would remain perpetually dark, as if caught in an eternal midnight. However, the world would not be invisible. As the high-energy particle wind slams into whatever thin atmospheric remnants or surface minerals remain, it excites the atoms, forcing them to glow with ghostly, luminescent light. Magnificent, multicolored auroras would dance continuously across the entire sky, lit by electric blue, emerald green, and deep violet sheets of radiation. The pulsar itself would appear in the sky not as a blazing golden disk, but as a tiny, blindingly bright point of blue-white light, flashing thousands of times a minute with precise clockwork regularity. High-energy magnetic field lines would be traced in the thin air by glowing ionized gas, creating a shimmering, ethereal grid of light hanging over a barren landscape of irradiated rock. Worlds like Draga, Poltergeist and Phobeta show us that planetary systems can exist in the most extreme, unexpected corners of the universe. They prove that planets can coalesce from the shattered debris of a supernova explosion and endure in the shadow of a stellar corpse. But they also stand as grim monuments to the destructive power of physics. Bound to a dead star that sweeps deadly X-ray beams and relativistic particle winds across their frozen surfaces every few milliseconds, these pulsar planets are perpetual ghost worlds, trapped forever in a beautiful, lethal dance with the dead. On Earth, our daily experience with matter leads us to believe that physical states follow simple, intuitive rules. Water freezes into cold, slippery ice at 32 degrees Fahrenheit and turns into vaporizing steam at 212 degrees. Carbon exists as soft graphite in a pencil lead, while rare, precious diamonds are formed only through extreme geologic luck deep beneath the crust. But when we venture into the broader laboratory of the universe, planetary gravity, extreme thermal energy, and crushing pressures distort these familiar thermodynamic rules. Across deep space, planets exist where exotic states of matter break everyday physics. Worlds where water stays solid as scorching ice at hundreds of degrees, and where entire planetary mantles are built out of solid diamond. To understand the strange physics of burning ice, we must look at Gliese 436b, an extraordinary exoplanet located roughly 33 light-years from Earth in the constellation Leo. Gliese 436b is roughly the size and mass of Neptune, making it a warm ice giant. It orbits its host star, a cool red dwarf, at a distance of just 1.5 million miles, completing a full orbital revolution every 2.5 Earth days. Because of its extreme proximity to its star, the upper atmosphere of Gliese 436b is continuously baked by stellar radiation, driving atmospheric temperatures up to nearly 800 degrees Fahrenheit. Under normal atmospheric conditions, like those found on Earth, water at 800 degrees Fahrenheit would instantly flash into high-pressure steam or superheated thermal vapor. Yet spectroscopic observations and gravitational mass radius calculations reveal that a massive portion of Gliese 436b consists of solid water ice. This apparent physical paradox, a world enveloped in solid ice while burning at 800 degrees, is made possible by the incredible force of gravity and pressure. To understand how solid ice can exist at temperatures that should melt steel, one must examine the phase diagram of water. In our everyday life, the ice we put in drinks is known to science as Ice 1, a low-pressure crystalline structure where water molecules bond together into a delicate, open hexagonal network. Because this hexagonal lattice contains a large amount of open space between molecules, ordinary Ice 1 is actually less dense than liquid water, causing ice cubes to float in a glass. However, when water is subjected to extreme gravitational compression, the open hexagonal lattice of Ice 1 collapses completely. As you increase the surrounding pressure to tens or hundreds of thousands of times Earth's sea level atmospheric pressure, water molecules are forced into increasingly dense arrangements. The hydrogen bonds are crushed and forced to reorient, pushing the substance through a series of distinct crystalline phases known as Ice 2, Ice 3, Ice 5, and beyond. Deep beneath the atmospheric outer layers of Gliese 436b, the immense mass of the overlying hydrogen and helium envelope exerts a crushing downward gravitational force. The pressure deep within the interior climbs to millions of atmospheres, or hundreds of gigapascals. Under this colossal pressure, water undergoes a profound structural transformation into a specific high-pressure crystalline phase known as Ice 10, a distinct high-pressure crystalline phase. In the state of Ice 10, the pressure is so immensely powerful that it overcomes the thermal kinetic energy that would normally cause water molecules to vibrate, break apart, and melt into liquid or evaporate into steam. The pressure literally locks the water molecules into an indestructible, hyperdense cubic crystal lattice. In fact, at the pressures required to create Ice 10, individual water molecules lose their traditional identity. The oxygen atoms are packed into a rigid, body-centered cubic grid, while the hydrogen nuclei, bare protons, are squeezed into fixed, symmetric midpoint positions directly between the oxygen atoms. The chemical bonds cease to be simple hydrogen bonds and become shared, symmetric covalent networks extending in 3 dimensions. As a result, Ice 10 remains completely solid even when heated to 800, 1000 or even 1500 degrees Fahrenheit. The thermal energy is simply unable to overcome the crushing mechanical force holding the atomic lattice together. If an observer could hold a block of Ice 10 in their hands, it would not feel like cold, slick ice. It would feel like a hot, dense, heavy rock, glowing faintly red with its own intense internal thermal radiation, while remaining rigidly solid to the touch. On Gliese 436b, this scorching ice mantle forms a giant core wrapped in a steaming outer atmosphere of hydrogen. As stellar winds blast the planet, the hot outer atmosphere evaporates into space, creating a massive comet-like tail of white hydrogen gas trailing over 9 million miles behind the planet. Gliese 436b travels through space like a giant burning snowball, a world held together by a core of hot, solid ice that defies everything we know about everyday chemistry. If a world made of burning ice challenges our understanding of water, an even more bizarre physical paradox exists on worlds composed largely of elemental carbon. Consider the extreme super-Earth known as 55 Cancri E, also named Janssen, located roughly 40 light-years away in the constellation Cancer. 55 Cancri E is a rocky world roughly 8 times more massive than Earth, with a radius twice as large. It orbits its host star at an astonishingly close distance, less than 1.5 million miles from the stellar surface, completing a full orbit in just 17 hours. Surface temperatures on the day side reach a searing 4,000 degrees Fahrenheit, turning the surface into an ocean of molten silicate and carbonaceous lava. However, The true wonder of 55 Cancri E lies deep beneath its molten surface. Stellar spectra of the host star show that it contains a much higher ratio of carbon to oxygen than our Sun. Consequently, the protoplanetary disk from which 55 Cancri E formed was rich in carbon, rather than the oxygen-rich silicates that formed the rocky planets of our solar system. On Earth, geology is dominated by silicon and oxygen compounds, forming quartz, feldspar, and silicate rocks, with carbon appearing only as a trace element in coal, limestone, and organic life. On 55 Cancri E, the planetary geology is fundamentally driven by elemental carbon. When a planet as massive as 55 Cancri E forms from carbon-rich dust, its interior becomes a giant chemical pressure cooker. At the surface, carbon exists as dense layers of graphite, the same black, greasy material found in pencil lead. But as you descend deeper into the interior of 55 Cancri E, the weight of the outer crust produces interior pressures exceeding tens of millions of atmospheres, accompanied by internal temperatures of thousands of degrees. Under these extreme thermodynamic conditions, carbon atoms are forced out of the flat hexagonal sheet structure of graphite. The extreme pressure forces the valence electrons of adjacent carbon atoms to overlap and hybridize into an optimal three-dimensional tetrahedral arrangement. This atomic transition converts soft black graphite into pure crystalline diamond. Astrophysical models estimate that at least 1/3 of the total mass of 55 Cancri E could consist of pure diamond. Deep beneath a dark surface crust of graphite and churning pools of liquid lava sits a diamond mantle thousands of miles thick. This is not a collection of tiny gem crystals buried in dirt. It is a continuous planetary-scale layer of solid diamond, weighing trillions upon trillions of tons. The heat deep within 55 Cancri E causes this diamond mantle to glow from within, radiating intense thermal energy outward toward the surface. Mountain ranges of compressed carbon and subterranean veins of pure diamond would stretch across the deep mantle, surrounded by liquid carbon fluids under pressures so vast that they behave as dense metallic liquids. Worlds like Gliese 436b and 55 Cancri E demonstrate that our terrestrial definitions of solid, liquid, and gas are merely tiny islands within a vast sea of physical possibilities. When pushed to the extreme limits of gravity and pressure, water can burn as a glowing solid crystal, and entire planets can transform their carbon cores into glittering diamond worlds. Deep space proves that when physics is pushed to its outer limits, nature creates realities far stranger than fiction. Up to this point, our journey through the dark side of the cosmos has focused on physical planets, distorted spheres of hot ice, liquid iron rain, and burning diamond rock. Yet, some of the most horrifying environments in the universe do not possess solid surfaces or visible atmospheric boundaries. Instead, they are invisible force fields generated by dead stars and collapsed space-time. These invisible monsters operate on scales that defy human intuition, warping time itself or wielding magnetic forces so immense that they tear the fundamental building blocks of matter apart at an atomic level. To witness the first of these invisible horrors, we must look toward the ultimate abyss of general relativity: black holes. A black hole is born when a massive star exhausts its nuclear fuel and collapses under its own crushing gravity, compressing its entire mass into an infinitely dense point known as a singularity. Surrounding this singularity is the event horizon, the absolute point of no return, beyond which the escape velocity exceeds the speed of light. While the deadly gravitational pull inside the event horizon is well known, the invisible hazard surrounding a black hole is its ability to distort time itself through gravitational time dilation. Albert Einstein's theory of general relativity proved that space and time are fused into a single four-dimensional fabric called space-time. Massive objects warp this fabric, and gravity is simply the curvature of space-time. The closer an object gets to a deep gravitational well, the more severely space-time is stretched, causing time to move significantly slower relative to an observer far away in flat space. Imagine a hypothetical planet orbiting close to the event horizon of a supermassive black hole. On such a world, the immense gravitational potential creates an extreme time dilation effect. A single hour spent on the surface of this planet would correspond to decades or even centuries passing for the rest of the universe outside the black hole's influence. If an astronaut were to step onto this world for just a brief visit, they would return to their spacecraft to find that centuries had swept across the galaxy. Entire civilizations would rise and fall, stars would burn through their nuclear fuel, and generations would fade into history while the astronaut experienced only 60 ticks of a watch. However, surviving near a black hole's event horizon is a physical impossibility for any planet or human. Long before time dilation becomes the dominant experience, an invisible gravitational gradient executes a brutal process known as spaghettification. Because gravity drops off rapidly with distance, the side of a planet or an object facing the black hole feels a vastly stronger pull than the side facing away. As a world approaches the event horizon, this differential force stretches the planet vertically into a long, thin string of material while compressing it horizontally. Solid rock is pulled apart like soft dough, the core is ruptured and the planet's constituent atoms are stretched out into a stream of subatomic particles before being swallowed by the singularity. Time itself appears to freeze at the event horizon from the perspective of an outside observer, trapping the light and energy of the falling debris in an eternal invisible grave. If black holes manipulate the fabric of space and time, the second category of invisible cosmic threats warps the fundamental structure of quantum physics. Magnetars. A magnetar is a rare, ultra-dense type of neutron star created during the collapse of a massive star with a specific, rapid spin rate. Magnetars are relatively small, measuring only about 12 to 15 miles across, but they pack more mass than our Sun into that tiny sphere. What makes a magnetar the most dangerous magnetic entity in the cosmos is its magnetic field. A magnetar possesses a magnetic field strength measuring up to 1 quadrillion Gauss. To put this staggering number into perspective, Earth's natural magnetic field, which deflects solar winds and guides compass needles, measures about 0.5 Gauss. A typical refrigerator magnet measures roughly 100 Gauss. The magnetic field of a magnetar is 1 trillion times stronger than Earth's magnetic shield, making it the most powerful magnetic environment in the entire universe. The invisible magnetic field surrounding a magnetar is so ridiculously intense that it breaks the ordinary laws of atomic structure and chemical bonding. Under normal circumstances, an atom consists of a positively charged nucleus surrounded by a spherical cloud of negatively charged electrons. The chemical bonds that form all matter, from solid rock to human deoxyribonucleic acid, rely entirely on the shape and interaction of these spherical electron clouds. However, if an object or planet strays within a few thousand miles of a magnetar, the invisible magnetic force completely overrides the electrostatic forces holding atoms together. The magnetic field exerts such immense pressure on charged particles that it forces the spherical electron clouds of every atom to deform violently. The electrons are squeezed into hyper-thin, needle-like cylinders oriented along the magnetic field lines. At a field strength of 100 billion Gauss, atoms are compressed into narrow tubes that are hundreds of times thinner than their normal atomic radii. Because the electron clouds are flattened and stretched into needles, atoms lose their ability to share electrons or form covalent bonds. Chemical compounds instantly dissolve. If a spacecraft or an incoming planet were to approach a magnetar, its molecular structure would not merely melt or burn, it would mechanically disassemble. The chemical bonds holding metals, plastics, and biological tissues together would instantly snap. The material would be dissolved into a gas of stretched, highly polarized individual atoms flowing along invisible field lines like iron filings. Furthermore, magnetars are prone to starquakes, sudden violent ruptures of their superdense iron crusts caused by intense magnetic stress. When the crust of a magnetar shifts by even a fraction of a millimeter, it releases a massive burst of magnetic energy in the form of high-energy gamma rays and X-rays. In 2004, a giant flare from the magnetar SGR 1806-20, located 50,000 light-years away on the far side of the Milky Way, struck Earth's upper atmosphere. In less than 1/10 of a second, it released more energy than our Sun produces in 100,000 years. Even from 50,000 light-years away, the invisible blast physically compressed Earth's ionosphere and blinded space-based sensors. If that same magnetar flare had occurred within 10 light-years of Earth, it would have stripped away our ozone layer instantly, sterilizing the surface. Black holes and magnetars demonstrate that the most lethal threats in the universe are often entirely invisible to the naked eye, whether warping time into a distorted trap near an event horizon, or stretching atoms into useless needles across thousands of miles of empty space. These invisible force fields show that the dark side of the cosmos possesses weapons that operate far beyond the surface of any alien world. We do not need to look thousands of light-years away to see the terrifying nature of the cosmos. The nightmare worlds we have explored are a direct preview of Earth's ultimate destiny. In roughly 5 billion years, our golden sun will exhaust the hydrogen fuel in its core. As it begins fusing helium, its outer layers will swell dramatically, transforming our peaceful star into a bloated red giant. As the stellar furnace expands, its blistering heat will incinerate our home planet. Earth's surface temperatures will skyrocket, boiling away the oceans until every sea, lake and river vanishes into vapor. Intense solar winds will strip away our protective atmosphere, leaving behind a barren, airless shell of scorched stone. Earth will no longer be a vibrant oasis of life, but a lifeless, glowing rock orbiting inside the outer atmosphere of its dying sun, joining the tragic ranks of the universe's most horrific hellscapes. Exploring these terrifying alien worlds reveals a profound truth. Our universe is overwhelmingly hostile to life. Earth is not the cosmic norm, but a rare, fragile miracle floating through a vast sea of violence and chaos. Every supersonic glass storm, lava ocean, and irradiated stellar remnant reminds us just how precious our calm blue haven truly is. Today, we have explored the dark side of the cosmos, the most terrifying planets and worlds ever discovered by science. If you enjoyed this cosmic journey, please like this video and subscribe to the channel. Let us know in the comments below, where and when are you watching this from right now? Until next time, keep looking at the stars, but remember, the dark is always looking back.